Bismillahirrahmanirrahim. So today's topic is one sample t-test with examples. My name is Dr. Taimia Ayub, and I will be giving this presentation under kind supervision of my supervisor, Professor Dr. Saira Afzal. So we will start with the quote of the day, which is, "Every day is a fresh start." So this is the outline of today's presentation, in which we will first do revision of previous terms. Then we will start with the concept of t-test, then one sample t-test. What do we mean by degree of freedom, t-table, examples of one sample t-test, and then strengths and weaknesses of one sample t-test, and followed by the MCQs at the end. So the learning objectives of today's presentation is that we are going to explain the purpose and assumptions of a one sample t-test, identify appropriate situations for using one sample t-test, and perform a one sample t-test with examples and avoid common pitfalls in the hypothesis testing for this test. So these are some of the revisions of the previous concept. So what do we mean by population? Population refers to the entire group of individual or objects that are being studied. For example, all pregnant women in Lahore. Then what is a sample? Sample is a subset of the population. For example, 100 pregnant women from selected clinics in Lahore. Then we come to parameter. What is a parameter? It is a numerical value describing a characteristic of the entire population. Average hemoglobin level of pregnant women in Lahore. It is denoted by the word mu. It is a Greek word. Then we came to the term statistic. Statistic is a numerical value describing characteristic of the sample. Sample mean hemoglobin of 100 pregnant women from selected clinics in Lahore. It is denoted by sigma x. Now we come to the Okay, so now here I just wanted to revise that in statistics, what is the difference between statistics and parameter? For example, mean is denoted by x bar for sample population, and it is denoted by mu for the whole population. Similarly, there are going to be differences in variances and standard deviation and proportion for sample population and for the whole population. So now we come to the concept of the hypothesis. We have done this many times, so I'm going to make it very quick and focus on the most important parts of the previous concepts. Hypothesis is a testable statement or assumption about a population parameter that is evaluated using statistical methods. So there are two types of hypothesis, null hypothesis or alternate hypothesis. Null hypothesis is denoted by H naught. It assumes no difference between two groups. It always has equal to sign in its equation. Alternate hypothesis is denoted by H1 or HA. It assumes that there is some difference between two groups. It does not have equal to in its equation. So now we come to types of error. There are two types of error. Type 1 error, which is also called false positive. And then there is type 2 error, which is false negative. What is type 1 error? It is rejecting null hypothesis when it is true. And type 2 error is failing to reject null hypothesis when it is false. So in this table, you can see that on the upper part, it is the reality of the situation is given that null hypothesis is true or null hypothesis is false. And then on the left side, what is our decision regarding the null hypothesis? We reject null hypothesis or fail to reject null hypothesis. If the null hypothesis is true and we reject null hypothesis, it is called type 1 error. And then if null hypothesis is false and we fail to reject null hypothesis, it is called type 2 error. So this is a fun way to describe type 1 and type 2 errors. So in which case you can see that what is happening here is that the verdict is by the judge and the reality is up there. If the person is genuinely innocent and we jail him, then it is kind of like type 1 error. And it is more dangerous than the type B or type 2 error. And the other thing is that we are going to put a person who is done some crime, but we fail to prove them criminal, so they are set free. So always remember that type 1 or type alpha error is more dangerous than type B or beta error, because putting someone in jail who is innocent is more dangerous or is more criminal. So now we come to another important term, which is critical region. What is critical region? In statistics, a critical region is a range of values for a test statistics that, if obtained, would lead to rejection of the null hypothesis. So basically, critical region is that region, if our calculated test statistics fall in that region, we will say that we are going to reject the null hypothesis. Critical region is also known as rejection region. So it is the rejection region of the null hypothesis. So we will start with the two-tailed test. Two-tailed test has two critical regions or two rejection regions. You can see there on the right side also and on the left side also. So the null hypothesis is, in this case, is that two means are equal, and the alternate hypothesis is that two means are not equal. Simple as that. So the acceptance regions of the null hypothesis is in the center, and the critical or the rejection region of the null hypothesis are on the two sides. Then we come to the one-tailed test, which is first is the left-tailed test, in which it says that the tail or the rejection region or the critical region is on the left side, and the acceptance region is the rest of the whole region is known as acceptance region. And in the right-tailed test, the rejection or the critical region is on the right side, and the acceptance region is the rest of the whole region in the curve. So now we come to the t-test. What is t-test? It is a statistical test used to compare the means of two groups to determine if they are significantly different from each other. So there are some important conditions for the t-test, that it is used when the sample size is small. Usually n is less than 30. The population standard deviation is unknown. It is one of the most important differences between t-test and z-test, that in t-test, the population standard deviation is unknown. And then the third point is that we assume that the data is normally distributed. So now we have three types of t-test: one sample t-test, independent or unpaired t-test, dependent or paired t-test. So in this presentation, I'm going to focus on one sample t-test. One sample t-test is used to compare continuous data with a standard given value. It compares mean of a single sample to a known population mean. The formula is, t statistics for this is x bar minus mu divided by s divided by under root n, where x bar is the sample mean, mu is the population mean, s is the sample standard deviation, and n is the sample size. So this figure shows that in one sample t-test, we are going to see if there is any difference between a group of people and their that specific value we are going to find out and compare it to the population parameter or population value. Degrees of freedom is another very important concept, which we are going to see later on how we are going to use it. But for now, we are going to tell you the definition and how degrees of freedom, different degrees of freedom lead to different variations. Degrees of freedom represent the number of independent values that can vary in a statistical calculation without violating any given constraints. It's a difficult definition. I will try to explain it further. The t distribution changes shape depending on the degrees of freedom. Lower degrees of freedom lead to heavier tails, meaning more uncertainty. Higher degrees of freedom means t distribution becomes closer to normal distribution. So when you look up the critical t value, you need to know the degrees of freedom to find the correct value in the t table. So I'm going to describe degrees of freedom with this figure. I hope it will become more clearer. So you can see that the red line distributes, tells us the degrees of freedom with T distribution with 10 degrees of freedom. So you can see that the tails of this curve are thicker, and the central part is more towards the zero line. And now if we are increasing the degrees of freedom with the blue line, you can see with 20 degrees of freedom, the central part is going up and the tails are becoming more narrower or more lighter. This is the term we use, that the tails are becoming lighter with increase in degrees of freedom. And with the red line, you can see that the tails are becoming heavier with the less degrees of freedom. And this black line is showing T distribution with infinite degrees of freedom. So when the sample is approaching a very larger size or infinite degrees of freedom, the T distribution will become equal to the standard normal distribution. You can see that the black line is representing the standard normal distribution, and also it is representing the T distribution with infinite degrees of freedom. Now, there is another figure. I will just quickly go through it. The yellow line is showing us degrees of freedom, T distribution with degrees of freedom 1. As you can see, it has very thick tails, and the central part is...
डॉक्टर ताइमा प्लीज पिछला वाला दोबारा बता दें, पिछला वाला ग्राफ.
Sorry.
Thank you.
So this is the T distribution when the n is small and sigma is unknown. So I want to highlight the fact that there are many different types of graphs of T distribution. Every degree of freedom has its own T distribution. That is the main difference. With z-test, I will show you later that z-test has only one kind of distribution. But for t-testing, every degree of freedom will have their own graph. So I want to emphasize here that the T distribution with 10 degrees of freedom is the tails are heavier, they are more area under the tails, but less area under the central part. And similarly, for example, T distribution with 1 degree of freedom will be here, and its tails will be here. If you can imagine it, it will be shown later on also. And when the degrees of freedom increase, the shape will become more narrower in the central part, and also the tails will become more thinner. And when it approaches the infinite distribution, which is equal to the standard normal distribution, which is the black line, the tails will become even more thinner or lighter, and the central part will become more narrower and will increase in its area. This is the same graph. Yes, this is the same graph. If you can have a look here, that this yellow line is showing the T distribution with one degrees of freedom. You can see here that the yellow area has many thicker tail. On the both sides, the tails are thickest when the line is yellow, which is 1 degree of freedom, and the central part is the most less. When we increase the degree of freedom from 1 to 3, the central part is increasing in size, and the degrees and the tails are becoming more thinner. The yellow and then the green tail become thinner. And then when we increase the degrees of freedom to 8, it again becomes, it again become more narrower here, and the tails are becoming lighter. When the degree of freedom is 20, you can see it becomes pretty close to the standard normal distribution of black color. So the purple color and black color, you can see they are very similar, but still there is difference. So the standard normal distribution is approached when the degrees of freedom are infinite, or still, we will see later on in the table, if there are 100, 1,000, 500 sample size, it still become pretty close, like really, really close to the standard normal distribution. But we usually say that when degrees of freedom are infinite or the sample size is infinite, then T distribution approaches or is equal to the standard normal distribution. So this is another important concept which I wanted to highlight here, which is the concept of the t-test table. So this is when we are doing the t-test or one sample t-test manually, we are actually comparing our value, which we will calculate from the formula, to this table. So it is very important. When we are doing it via any software like SPSS, we don't need to work on this. But when we are doing it on the via this manually, it is a very important table to find out, t-test table. So we can see here that the degrees of freedom are on the left side of the table. You can see 1, 2, 3, 4, 5, 6, 7, 8. It leads to 1,000. And similarly, on the upside, we have the value of alpha. In this table, they have given us different values for one-tail test or two-tail test. And then this is the T.50, T point. So usual value of alpha, if we can just focus on that, for um, one tail and two tail is 0.05. We assume the value of alpha as 5%, which equals to 0.05. And then if for one tail test and for two tail test, we divide that value into two. So these are the two basically tables in which we focus while we are finding the value of t distribution. So we will see practically how we will equal. And if you can see on the bottom line that this is the z value. Z value remains the same as compared to the t distribution, which is changing because of degrees of freedom, if you can see. So the z value is the equal to the normal distribution value. So you can see that when the t distribution or the t degrees of freedom is 1,000, it nearly becomes equal to the z value, but not completely still. For example, there is a difference of 0.675 to 0.674, but here it's pretty much same. So there are many other decimal points after these three, so we are focusing on that. So I just wanted to give the concept of this. So we will move on to our examples now. So one sample t-test with examples. So all the steps we have discussed below or the important terms, we are going to see how practically we use these for using our t-test. So example 1, a nutritionist claims that the average daily protein intake for adults male in a population is 60 grams. You want to test this claim. You collect a sample of 10 adult males and their average protein intake turns out to be 65 grams with a sample standard deviation of 8 grams. So we have four values here. Population mean, which is assumed to be 60 gram, our sample mean of protein intake, which is assumed to be 65 gram, sample number or n is our 10, and standard deviation of sample is 8. So please keep this numbers in mind. So we will first set up the hypothesis. So the null hypothesis will be mu is equal to 60 and the alternate or H1 hypothesis will be mu is not equal to 60. This is a two-tailed test because we are checking for any significant difference, not just more or less. So equal to 60 or not equal to 60. This is the so this is two-tailed test. So sample size is our n is equal to 10. Sample mean x bar is 65. Sample standard deviation s is 8. Hypothesized population mean is or mu naught is 60. So this is the formula for our one sample t-test. So we are just going to put all the values, and I would encourage you when you have time to please practice these questions also. So sample mean 65 minus population mean 60 divided by standard deviation of sample 8 divided by underscore sample size, which is 10. So this comes out to be 1.976. So now we are going to find the critical t value from the table. So first we will have to know the degrees of freedom. So in this, the degrees of freedom for one sample is n minus 1. So our sample size is 10. So 10 minus 1 is 9. So our degrees of freedom for this question is 9. Significance level for two-tail test. So significance level is usually calculated as 0.05. But for two-tail test, we divide it by 2 for each tail. So there are two tails, so we will divide 0.05 by 2. So we will have 0.025. So we are going to look up the t critical value for 9 degrees of freedom in alpha divided by 2, 0.025 in the t table. So I will show you how we arrive at this critical value of plus minus 2.262. I want you here to look at this plus and minus symbols, and I will explain them further that why we have plus and minus symbols here. So this is the t-test table. And first we are going to look at the degrees of freedom here. So they come out to be 9. So we will go in this line. And from the top, we are going to have for two-tailed 0.05 or as we calculated 0.025. for the our significance level, and it comes here to be these two lines coincide as 2.262. So this is the T critical value of 2.262. Why I have the plus and minus signs, I will explain in the next picture. Okay, so now we have to make the decision. So we will reject null hypothesis if T is less than minus 2.262 or T is greater than 2.262. It is easier to understand it here. So this is the T distribution curve for 9 degrees of freedom. Okay, so this is the central value. These are the two critical regions. So the plus 2.262 is the positive critical region and the minus 2.262 is the negative critical region, because it is a two-tailed test. So you have to remember that there are going to be two tails. So one tail starts from the positive 2.262 and the other tail starts from the minus 2.262. So if our calculated T value falls anywhere in the middle region between minus 2.262 to plus 2.262, we will not reject the null hypothesis. Otherwise, if it is more, our calculated T value is more than 2.262 or less than minus 2.262, so it will come here or here. So we will reject the null hypothesis. So our calculated T value is 1.976, which we calculated from that formula, and we put in the values which were given in our question. So it comes down to here, it comes 0 and plus 2.26. So it comes here. So that is why we will not reject the null hypothesis. And the correct statistical term to say is that we do not reject the null hypothesis. We can't, it is not wiser to say that we accept the null hypothesis. It is more statistically correct to say that we do not reject or we fail to reject the null hypothesis. So I hope it is more clear. So now we come to the conclusion that there is not enough evidence that at 5% significance level to conclude that the mean protein intake is different from 60 gram of the population intake. Okay, so now we come to the second example. I will emphasize on the terms which if we keep them in mind, it will be easier. So let's go through the second example. A local public health department introduced a physical activity program to promote healthier lifestyles. National guidelines recommend at least 150 minutes of moderate activity per week. To assess the program's impact, a random sample of 15 adults was surveyed 1 month post-intervention. The average weekly activity was 165 minutes with a standard deviation of 20. The department aims to determine at the 5% significance level whether the intervention significantly increased physical activity. So again, we have national guideline value of 150 minutes, and then we took sample size of 15, and the average weekly activity level or the mean value for sample was 165 minutes with standard deviation of 20. Okay, so we will keep these values in mind. So what we want to figure out that if intervention significantly increased physical activity. So this word is suggesting that we are going to go with one direction and not two direction, or not being very specific. So this is a right tail test because we want to know if the average time is greater than 150 minutes. So the null hypothesis or H naught is mu is equal to 150, or alternate hypothesis is H1, mu is greater than 150. So again, these are the values which we are going to put. This is the X bar, which is 165 minus mu population value of 150. Then we have sample size of 20, standard deviation of 20 divided by sample of 15. So this value, we calculate it to be 2.905. So again, we will have to find the critical value from our table. So again, we will calculate the degrees of freedom. So the degrees of for this one sample will be n minus 1. So our sample size is 15. So 15 minus 1 is 14. So our degrees of freedom is 14. So alpha is equal to 0.05 for a right tail test. As it is a one tail test, we will not divide 0.05 by 2. We will keep it as 0.05. And from the table, we are going to look for degrees of freedom 14 and then alpha value of 0.05 and then see where these two values coincide. So these values will coincide at 1.761, but I want to show here how we are going to do it practically. So from the left side, we will look at the degrees of freedom. Then we go to the 14 because this is our calculated degrees of freedom. And then we have the significance level of 0.05 for one tail test. And then we come here and they coincide as 1.761. So decision rule is that we will, if our calculated value is greater than T critical value from the table, we will reject null hypothesis. In our case, the calculated value is 2.905 and our critical value was 1.761. Please note here that as it was a one tail test, there was no positive or negative sign. There was only positive sign because it was right-sided one tail test. So our calculated t value, which we calculated from the formula, comes out to be 2.905, which is greater than 1.761. So we will reject the null hypothesis. So conclusion, there is statistically significant evidence that the public health intervention increased the average physical activity level beyond the recommended 150 minutes per week. So now we come to the strengths of one sample t-test. Strength of one sample t-test is that it is simple and easy to apply. It is straightforward to calculate and interpret, especially with softwares like Stata, etc. It is useful for small sample sizes. Unlike z-test, the one sample t-test is specifically designed to work well with small samples n less than 30. It does not require population standard deviation, which I have emphasized before that this is the main difference between z-test and t-test. It is widely applicable, especially in fields like public health, psychology, etc. It is supported by many statistical tools and foundation. It is the foundation for other tests like paired t-test and independent t-test. They work on the same principle of one sample t-test. So some of the weaknesses of one sample t-test, it assumes normality of the population. It assumes that the data is approximately normally distributed, especially important for small sample sizes. It is sensitive to outliers. A single extreme value can distort the mean and standard deviation. It only compares to a fixed value. It can only test if a sample mean differs from a known or hypothesized value. Assumes random and independent sampling. It has limited inference. It does not give information about variability between groups or over time. It just tells us simple yes or no answer. It is less robust with very small samples. While it is designed for small sample sizes, but when n is very low, for example, less than 10, it does not work very well. So now we come to the multiple choice questions. So the first question is, which of the following best describes the purpose of a one sample t-test? A, to compare means of two independent groups. B, to test association between two variables. C, to determine if a sample mean differs from a known or hypothesized population mean. D, to assess changes in the same group over time. E, to measure correlation strengths between variables.
Charlie? C.
Charlie.
Yes, the answer is C. Yes. Question number 2. Which of the following is an assumption of one sample t-test? A, the data is paired. B, data is nominal. C, data is normally distributed. D, data large sample size. Or E, equal variances between groups.
Charlie.
C.
Yes,
Normal.
it assumes that the data is normally distributed. So a researcher wants to test if the average hemoglobin level in a population of pregnant women is significantly different from the national standard of 12 gram per deciliter. Which test should be used? A, two sample t-test. B, chi-square test. C, one sample t-test. D, ANOVA. Or E, z-test.
C.
One sample.
Yes, so
T-test.
one sample t-test. When we are
One sample.
going to compare our
C.
sample size with the national standard. So the question 4 is, what is the null hypothesis in a one sample t-test? A, the sample mean is less than the population mean. B, the sample mean is equal to the population mean. C, the population mean is unknown. D, the variances are unequal. Or E, the data are dependent.
B.
Yes, B, the sample mean is equal to the population mean, or that there is no difference between these two groups. Question number 5. A public health nurse claims the average number of prenatal visits is 7. A sample of 20 patients shows a mean of 6.5 visits. Which statement is true? A paired t-test should be used. No, B, no hypothesis testing is needed. C, a one sample t-test can be used to test the claim. D, only median values should be used. E, sample size is too small to test.
Charlie.
Yes.
C.
So we will use the one sample t-test. Yes. What happens if data are not normally distributed in a small sample for a one sample t-test? The results are still valid. B, the test becomes more powerful. C, the assumptions are violated. Results may be invalid. D, the test becomes a z-test. E, it is converted into a chi-square test.
C.
Yes, the results are still valid, but there is if the data is not normally distributed, then answer is C. The assumptions are violated and results may be invalid, because we are going to base our whole test on the assumption that the data is normally distributed. Question number 7. A health researcher wants to test whether the mean cholesterol level in a rural community is different from 200 milligram per deciliter. What is the alternative hypothesis? Mean is equal to 200,